Hey guys, this is Andrew with HKN, and today we're going to be talking about how you take a system, put it into state space, and then some fancy things you can do in Matlab with when it comes to analyzing state space. So the first thing I want to talk about is just to refresh the general form of state space. So you have a vector of state variables, x, and an input, u. And the general form is that the derivative of each states is equal to some matrix A, which is n by n if you have n states, times x plus an n by 1 vector times your input. If you have one input, it would be n by p if you have p inputs. And then y being your output would equal to c times x, which is usually your output is one thing. But if you have, say, q, this would be n by q, or sorry, q by n, so that this is an n and you get a q on the output. And this would be q by 1, so that you can multiply, or q by p, so that you can get your same number of outputs for inputs here. So in order to work with state space, we have a video about that. If you don't remember much about it, you can look at it. It'll be above my head here somewhere. But I'm assuming that you know how all this works, essentially. So we're going to go right into creating the equations of motion here. So we need state variables that we can write this with. So let's write the equations of motion first, and then we'll see what state variables we need. So the good thing to write is the sum of the forces equations for these two guys. So that kind of encapsulates everything of what's going on here. And we have nice laws for the forces of a spring and a damper. So that's not anything crazy for us. So let's do it. So we have here, we'll have x1. So we'll say that this block is going to be x2. And this block will be x1. And we'll say that moving to the left will be positive. So we want the sum of the forces equals mass times acceleration. So for us, that means that we have to say that we have to have m1 x1 double dot is equal to, so that's mass times acceleration of block 1. And so now we actually have to literally just sum the forces. So in the positive direction, we have this spring pulling us. And it's going to pull us by the difference between K2 and K1. So if, X1 and X2. So if X2 moves to the left here, X1 has to move the same amount. And if it does, there'll be no force. But if it moves less, there will be a force. So it's just K times X2 minus X1. And we'll expand that later. And to the right, we have pulling a damper here. So as we move to the left here, assuming that we're moving in the positive direction, the damper will slow us down. So it actually always slows you down in the direction of your velocity. So if we're moving to the right, we get damped as well. So pushing in or pulling out will damp our motion. And it actually does it proportionally to velocity. So we're going to have minus the damping coefficient times x1 dot. And so that should be our equation of motion for mass 1. So this is our first state equation. We have two blocks here, so we're probably going to have two of these equations. And if we write out this state equation with it equaling 0, then we end up with, or equaling x1 double dot. So we get x1 double dot is equal to k over m1 x2 minus k over m1 x1 minus d x1 dot. And so this is our first equation of motion in the form that we can put it into state space. The next one we're going to do is we're going to do a sum of forces analysis on m2. So if we do that, we end up with m2 x2 double dot. So that is mass times acceleration of x2. Well, the first thing that we have is we have a force here, F of t, pulling on m2. Or it could be pulling or pushing, but we're defining positive as being to the left again. So we just get F of t, just a force. Then in the opposite direction, we have k pulling us to the right, the difference between how much x1 has moved and x2. So we get the same force here, k x2 minus x1. And so you'll see it's just the negative of the term here. And that makes sense to us because we need to have equal and opposite forces coming from this spring. So just double checking to make sure that ends up correctly, and it looks like it does. Yes, OK. So now we have to do the same thing, put it in the same form. So if we do that for equation 2 here, we get x2 double dot is equal to f of t over m minus k over m x2 plus k over m x1. So remember that the general form just has a single derivative in it, and we have equations here that involve the first and second derivatives of our functions or of our state variables. So things that we can that are our state variables here would be x1 and x2, because these are things we don't know that we're writing our equations in terms of. But we have a second derivative of it in there too. But luckily, we can just make the derivatives a state variable, and it'll also work out fine. So we're going to pick our state matrix, our state vector, to be x1, x1 dot, x2, and then x2 dot. So the derivative of this state vector would be x1 dot, x1 double dot, x2 dot, and then x2 double dot. Just take a derivative linearly with each term in there. And so now we have to write our terms, our values in terms of the things given. And so we also have f of t as an output here, and say that we want our output to be the position of x1. So that is your y. Y is x1. So we can very quickly do y equals x1. So this is the same state vector. So we have x1 dot, x2, and then x2 dot here. And so this is a very easy state vector to make for the output. So for C, it's just we want to get 1, and we don't want anything else. So we just get zeros. And so the next thing we want to do is we want to construct this A matrix here. So in order to do that, we need to look at the equations of motion. But the two that we can do very quickly are x1 dot in terms of these guys, because we have an x1 dot here. So that means across the top, we just get 0, 1, 0, 0. We also have x2 dot in our state vector, and that's in the 4th position. So those are the two columns of the two rows of A corresponding to x1 dot and x2 dot. x1 double dot, very nicely, and x2 double dot we have equations for here and here. So we can put these guys in. So in the x2 slot, which corresponds to the 3rd position, and this is x1, we have k over m1. These should be m2s, by the way, if that wasn't clear. So we have k over m1 in the x2 position. So that means that here we should get k over m1. We have a negative k over m1 in the x1 position, which is here. So we should get negative k over m1. And then we have a negative d in the x1 dot position. And that probably should have an m1 under it, because I divided an m1 across everything. And then there is no term for x2 dot here, so that gets a 0. The second equation also does not have a term for x2 dot, so that's going to get a 0. And Otherwise, we have a negative k over m for x2, so that's the third position here. So we get negative k over m. And then we have a k over m2. Sorry. We have a k over m2 in the x1 position, so that goes here. And then there's no x dot equation, so that gets a 0. Put 0 fills in all these, just so you know they're not O's. All right, so we've now created our A matrix, but now we have this one extra term in our second term here. We have f of t divided by m2. And so our input is f of t. That's something that we can control, assuming that that's what the force applied is. So we have, and that's acting directly on x2 double dot. So that doesn't affect the other states, but it affects x2 double dot with a magnitude of 1 over m2. So the last thing we have to do is address what our D matrix should be. And that's going to be multiplying f of t. And so our D matrix, which because we have one input and one output, it'll be a 1 by 1 or a scalar. And the only thing that, and does f of t affect x1? No, it does not directly affect x1 in our equations here. x1, we've explicitly got it here. It's our state vector. So we don't need anything there. So D in this case is 0. And most of the time it is. It actually corresponds, the D matrix corresponds to the term of highest order in the numerator. If it matches the denominator, that means that your value at the current time is affected directly by your input, which often doesn't happen. And if the degree is any higher than the denominator, then you have a non-causal system, which doesn't make sense. So, or that we can't build. So this is the state space representation. So that means that we can do some Matlab here to try and make some sense out of this. So I'm going to show you two different ways to do the Matlab here. And so the first thing we're going to do is we're going to use the symbolic variable. So we're going to use syms, and we're going to declare variables for everything that we need to put into these matrices. So that's k, m1, m2, and d. So we have k, m1, m2, and d. I'm going to make that a capital K, just for to know that I'm always using capitals. And so what we want to do is we want to build these matrices. So the matrices here are A equals, so we have 0, 1, 0, 0. Then we have a new line, and we should have negative k divided by d, and then we should have negative k divided by m1. All right, okay, m1. And the next one is negative d divided by m1. And the next one is k divided by m1. All right, that looks good. And we need a 0 on the end there to make it the same length. Then we have 0, 0, 0, 1. And then we have k divided by m2. We have 0. We have negative k divided by m2. And then we have another 0. And then we close this off and suppress the output. So this is our A matrix. So the next thing we have to do is build the B matrix. So we have B equals, and this has to be a column vector. So that's going to be 0, 0, 0, and then 1 over m2. So we get 0, semicolon, 0, semicolon, 0, semicolon, and then we should get m2 to the negative 1. And then, is there something wrong with that one? Oh, I put it to the negative 2. Okay, that's wrong. It's a little far away today. Then we need to build C and D. Luckily, those are easy enough. So let's just do that very quickly. We get C equals 1, 0, 0, 0. And D is just a scalar 0. So now we want to do, so let's execute these to make sure that everything works out nicely here. All right, so we get, once this runs, we should get in our workspace, oh, I was writing lowercase k somewhere. Where was that? Looks here, capital K. Let's try that one more time. Oh, I did it again somewhere. I said I wanted to make it a capital so that I wouldn't make these mistakes, and I make these mistakes anyway. Nobody's perfect. All right, so those loaded fairly nicely. So we have, if we print out A here, we have our matrix. And so one thing nice that we can do with this is we know a formula for the transfer function of a system. So the transfer function from f to x1 is equal to, if you have a state space representation, it's equal to C Si minus A inverse B plus D. CSI minus A inverse B plus D. So we want to be able to calculate this. So let's just say TF equals, and this can very easily be done in Matlab, so we actually just need to declare one more symbolic variable as S. And so we want to declare TF is equal to C times parentheses S times I1, so I4, so we want a 4 by 4 identity matrix. And so you can get that from using EYE4. And then we want to subtract off A. And we want the inverse of this entire matrix. So I'm going to just type INV. You could also just do to the negative 1, and it should work as well. There are actually a bunch of different ways you can take the inverses of matrices in MATLAB. And then we need to multiply by our B matrix. And hopefully that all of these dimensions agree. I'm not going to add D onto this because it is a 0. So let's hope that this works out. Let's execute our file here. And OK, everything seems to have run. So let's take a look at what our transfer function is here. I'm going to clear the command window very quickly, and then we're going to take a look at what TF is. So let's print out TF in a pretty way. So let's simplify our transfer function. And then let's type this out in a pretty way. So it doesn't look like it's ending up looking very nice, but if you had values for all of these things, you could plug in and get a value for it. Apparently pretty doesn't look very pretty today. So, but either way, this is a function, and once it's actually just a scalar function. So if you plug in here for k, d, m1, and m2, you can get a transfer function. So the other thing that we can do very quickly is if we create these matrices with numbers, so let's just assume that all of our values are 1, because life is easy when everything is 1. We can say that A is 0, 1, 0, 0. We can say that the next row is negative 1, negative 1, 1, 0. We can say that our next row is 0, 0, 0, 1, and that the next row is 1, 0, minus 1, 0. And then we would have to have, oh, let me put that on the same row. I hit enter instead of semicolon. So that is our third row, and it should read 0, 0, 0, 1. OK, and it does. And it wants a space here because MATLAB is being finicky. All right, and then we want to suppress that output. And then B should equal to 0, 0, 0, 1. So we get 0, semicolon, 0, semicolon, 0, semicolon, 1. And then the other two are already scalars, so that's nice enough for us. So A, B, and C should be able to just be redefined this way. So if we execute all of this code, we should get A and B as doubles, which they are, and C and D as doubles. So now that we have A, B, C, and D, we can create a state space variable by doing SS. And we just then need to give it A, B, C, and D. And we'll call that our system. So we'll call that sys. So many S's in a row. And so we should be able to execute this. And now sys stores our matrices A, B, C, D as a variable that it recognizes as an LTI system. And so the last thing I want to show, which is nice, is that you can then take the transfer function of this, so we'll just redefine TF again, to be SS, or state space, to the number 2, TF, so state space to transfer function of the system, sys. And there was a capital S. And so if we execute this, oh, not enough inputs. Oh, okay, so it wants state space to transfer. So apparently you don't need system, you just need A, B, C, D. So that system variable works like having a transfer function variable, except it's written in state space. And this one will create a transfer function variable from our values. So we have a transfer function variable here. Apparently it doesn't like that today. I might have made a mistake in the syntax somewhere. But anyway, these commands will work. So you have state space to transfer function will output the transfer function for a given A, B, C, D. And SS will create a state space system variable, which you can then use things like step function and damping and polls and all of these different nice commands for systems on, which is always very nice to do. I seem to have made a mistake somewhere in the code, but these commands are the important things that you can do the same thing as you would do here in Matlab. So I hope you guys learned something and have a good day.